Today, I want to briefly explain seepage, a fundamental concept in geotechnical and dam engineering, but one that is often misunderstood. Seepage refers to the slow movement of water through a porous material such as soil or rock. It is important to emphasize that this is not surface flow like a stream or a river. Instead, seepage is a subsurface flow, moving quietly through the ground, driven by differences in hydraulic head, in simple terms, differences in water pressure or energy. Water will always move from a zone of higher pressure to a zone of lower pressure. This pressure-driven movement is what we observe as seepage. Now, seepage can only occur in materials that are permeable, materials with interconnected voids or pores that allow water to pass through. Examples include sand, gravel, and fractured rock. On the other hand, materials like intact clay have extremely low permeability, meaning water movement through them is very slow or almost negligible. To quantify this flow, we rely on the fundamental governing principle known as Darcy's law. For those who prefer the technical description, Darcy's law expresses the flow rate as Q equals K times A times I, where K is the permeability of the material, A is the cross-sectional area, and I is the hydraulic gradient. Why does this matter? Because this slow, often invisible seepage is responsible for developing poor water pressure, which can weaken the soil structure. If left unmanaged, the continuous movement of water can also lead to internal erosion, or what we call piping, particularly in dams, levees, and other hydraulic structures. So understanding seepage is not just an academic exercise, it is the first and most essential step in controlling it, ensuring the stability and safety of our earth structures. Seepage is the slow movement of water through porous materials, usually soil or rock. This movement happens under the influence of gravity and hydraulic gradients. In other words, water moves from a place of higher energy or pressure to a place of lower energy or pressure. It's a fundamental concept in geotechnical and environmental engineering because almost every structure we design interacts with the ground, and the behavior of water within that ground directly affects stability and long-term performance. So, let's go through how seepage behaves in different soil types. 1. Gravel and coarse sand. First, we have gravel and coarse sand. These materials have large grain sizes and relatively high porosity. Because the voids are big and well connected, the permeability is very high. What does this mean for seepage? Water flows very rapidly through these materials. Darcy's law applies very well here because the flow is usually laminar. Capillary rise is minimal, so they drain extremely efficiently. They don't typically develop high pore water pressures, but because flow is fast, the seepage volume can be large. One thing to watch out for is erosion or piping, especially if fine particles are present or if the hydraulic gradient becomes too steep. 2. Fine to medium sand. Next, we move to fine to medium sand. The grains are smaller, but porosity is still quite high. Water still flows relatively fast, although not as fast as in gravel. Capillary effects become more significant. You can get a capillary rise of about half a meter to a meter. One important point is that upward seepage in clean sands can lead to quicksand conditions or liquefaction when the hydraulic gradient exceeds the critical gradient, which is roughly equal to 1. These sands can also suffer from internal erosion if fine materials are washed out by seepage. 3. Silt. Then we have silt, with much smaller particles and high porosity. However, the permeability is low to moderate, meaning flow is slow. Capillary action becomes very strong here. You can get capillary rise up to several meters, depending on the soil structure. Because drainage is poor, pore pressures in silt tend to dissipate slowly, and saturated silts are easily eroded. This is where we can see phenomena like silt boils during flood events. Silt can also behave unpredictably. Under vibration it may soften, and in cold climates it may undergo frost heave. 4. Clay. Now let's talk about clay, which is very different from the previous soils. Clay has extremely fine particles and very high porosity, but most of the water is bound water, meaning it is not free to flow. As a result, clay has very low permeability. Seepage through intact clay is extremely slow, water may take years to move through thick clay layers. Darcy's law may not strictly apply at very low gradients because clay often exhibits a threshold gradient. This means water might not move at all until the hydraulic gradient reaches a certain minimum value. Clays also change over time. Swelling and shrinking can alter their permeability, and when they dry, desiccation cracks can create preferential flow paths. Another key point is that clays are anisotropic. Their horizontal permeability is often several times greater than their vertical permeability. 5. Layered or stratified soils. Finally, many natural deposits consist of layered soils, such as alternating sand, silt, and clay. In these cases, seepage becomes highly anisotropic. Water tends to move horizontally along the high permeability layers, while low permeability clay layers restrict vertical flow. This can create perched water tables above clay lenses, making drainage more complicated. The interfaces between soil layers are also vulnerable to piping if the hydraulic gradient is high enough, and because water tends to follow the easiest path, we sometimes see preferential flow paths forming, which can bypass the intended drainage or protection system. Let us now look at the different types of seepage that occur in dam engineering, and how seepage behavior changes depending on the type of structure and the foundation conditions. Even though dams are designed to retain water, the foundation beneath the structure is rarely perfectly impermeable. Because of that, water will always attempt to find a path through or under the dam. Understanding these paths is crucial for stability, safety, and long-term performance. The first type of seepage occurs in a typical earth embankment dam. Here, the water doesn't flow under the dam, it actually moves through the soil body itself. Inside the embankment, the seepage pattern is represented by what we call flow nets, which consist of flow lines and equipotential lines. The most important feature here is the phreatic line, which marks the upper boundary of the saturated zone. If this phreatic line emerges too high on the downstream slope, it can create wet spots, softening of the soil, and instability. That is why proper drainage, such as a chimney filter, toe drain, or drainage blanket, is essential to safely manage seepage within an earth dam. In this scenario, the water flow is smooth and continuous because soil is a porous medium. However, without proper drainage, the exit gradient at the downstream toe may become excessive, leading to piping or erosion. Now let's move on to the second case, seepage under a concrete gravity dam built on soil or rock. Unlike an embankment, a concrete dam is impermeable. Water does not pass through it, but instead finds its way beneath the dam along the foundation. Flow nets in this case show very sharp bending of the flow lines because the water must navigate around the rigid base of the structure. One of the key issues here is uplift pressure. As water seeps under the dam, it produces upward pressure on the underside of the foundation. If this pressure becomes too high, it can significantly reduce the dam's effective weight, potentially compromising stability. Another concern is piping beneath the dam if the foundation soils are highly permeable. So in this situation, engineers often install drainage galleries, relief wells, or grout curtains to control uplift and reduce seepage. The third seepage condition involves a dam equipped with a cut-off wall or grout curtain. This is a common method to improve the foundation's seepage resistance. The purpose of the cutoff is to extend the seepage path deeper into the ground, making it longer and more resistant. In the flow net, you'll notice that the flow lines bend sharply at the cutoff, and the equipotential spacing becomes tighter upstream. This indicates reduced hydraulic gradient downstream and a significant drop in uplift pressure. Overall, the presence of a cutoff greatly reduces total seepage, lowers the risk of piping, and improves the dam's safety. It forces water to travel a longer and more difficult path before exiting, which is exactly what we want in dam engineering.